Okay, well, so 1 p.m. Let's get moving here. I hope everyone joining us is joining safely and healthy. I know there's a lot going on, and yeah, these webinars are our way of bringing content to everyone when we're all stuck at home or at various different places around the world. So, just to spend a few minutes talking about the ASRG before we hand it over to our presenter here. Let me find control of my slide deck. There it is. So, a little bit about who's talking. I'm Brandon Berry. I'm the CEO at Black Harbor Cybersecurity, a service provider in automotive security since 2014. And with the ASRG, I am the Americas lead. So I help support Americas chapters in making sure that they can establish communities, and I coordinate some of these webinars. I try and help the ASRG thrive in North, Central, and South America. Sven, why don't you introduce yourself?
Yeah, hello to the audience. So my name is Sven Schran. In my professional life, I work for Robot Bosch GmbH. In my role there as Product Security Officer. So I'm involved in security nearly 4 years now. And for ASRG, I take over the role to drive the European market. So I'm a colleague of Brandon, have the same topics which Brandon drives in the Americas. I do it in Europe. So I coordinate the locations. I help to build new locations. I coordinate something and support the local leaders.
And Sven, thank you for all the work that you do. It's really just a reminder, ASRG is all volunteers here putting in really, really great effort to make these things happen all around the world. So a little about what the ASRG is all about. Before the pandemic, this is what meetups around the world looked like, where we had people joining and having great discussions and networking in person. But the three areas or pillars that the ASRG is trying to provide solutions for is knowledge, networking, and collaboration. Knowledge, providing platforms to enter the space and to become more educated on the space. Networking, meeting really great people all around the world, struggling with some of the same automotive security challenges as you may be, and then collaborating, making sure those same people are working together to push this industry forward. And we are all over the place. We have chapters really all around the world. Take a look at these chapters. If there isn't one locally and you think there's a automotive security community that would be interested, go ahead and reach out to us at hello@asrg.io. We would love to talk to you about starting a chapter in your location and help supporting you guys in getting started with an ASRG chapter and collaborating with people around the world. So just some of our upcoming webinars. We have our next webinar to be determined by Moabi. We'll be hearing from Rescure, Argus, Upstream, really a lot of exciting talks. And, I'm just looking at the agenda all the way out until April of next year. I mean, really, we'll be continuing these webinars for some time, and it's really exciting, some of the talks we have upcoming. If you want to present, reach out to us at cfp@asrg.io. We'd love to hear from you, and so would our community. Without further ado, I will hand it over to Andrew Tierney of Pentest Partners. He's going to be talking to us about over-the-air updates and the security around that. Andrew, I will give you the screen. It's yours.
Great. Thank you very much, Brandon. Hopefully everyone can hear me. Hopefully everyone can now see my slides. Just a really quick introduction to who I am. I work for a penetration testing company, and I focus on the things that aren't general purpose computers. So that's cars, ships, IoT, industrial control systems, and things like that. And one of my particular passions is reverse engineering things. So a few years ago, we had the goal of reverse engineering how the Tesla over-the-air firmware update mechanism worked. Why did we want to do that? Well, Tesla were kind of groundbreaking here. Even as early as 2013, 2014, their cars were taking over-the-air firmware updates for pretty much every component in the vehicle, and they were doing that regularly. So nowadays, a lot of auto manufacturers do over-the-air firmware updates, and it's gradually spread from core components like the telematics unit and the in-vehicle infotainment to other parts of the vehicle. But a long time ago, Tesla were pushing things out everywhere. And with the huge number of cars, we couldn't really see many people complaining about these firmware updates failing. So we really wanted to look into it and understand what was the security around that. How did it actually work? How were they managing to get this reliable enough that it was a viable thing to carry out updates for hundreds, thousands of cars? Now, this was 10 days of work in early 2018. So this is coming up to 2.5, 3 years ago. So some of it's kind of left my mind, unfortunately, but also a lot has changed since then. I'm going to talk about things like the VPN connection, the motherload, all these different aspects of Tesla. A lot of those have completely gone now. So this is a snapshot in time from 2 years ago. I'm also going to that come along when we're reverse engineering cars, things that you might not know about, things you might be interested to hear about, to do with code readout protection, recovering firmware from devices, and some of the techniques we use. So to look at a Tesla from a very high level, I don't know if you sat in a Tesla, there's a very, very large screen in the middle. That's called the CID, or Central Information Display. So that's kind of akin to in-vehicle infotainment, or an IVI in most vehicles. Just the screen is absolutely huge. You've also got what's called the instrument cluster, and that's familiar to all of us. That's the IC in Tesla terms. Again, that is another big LCD screen. So they're both big LCD screens connected to each other. That's what you see when you're in the cockpit of a Tesla. That big CID was groundbreaking when it first came out. Having a screen that large was unheard of. Now, based on what other people had already looked at in the Tesla, this is the vague architecture of the vehicle. Now, that central information display is huge. Behind that screen is a PCB, a circuit board, the size of the screen. It's absolutely massive. It contains something called the VCM, or Visual Compute Module, which is a specific module, processor module, developed by NVIDIA. That's connected using Ethernet through to another VCM in the instrument cluster. So they're both running these very, very powerful processor boards in them. That's connected via Ethernet, conventional Ethernet. There's a switch in there, an Ethernet switch, that also connects to a CAN gateway. So what that allows is the VCM in the CID to send messages through to that CAN gateway, which will then send CAN messages through to the rest of the vehicle. Now, for the Model S we were looking at, there were 5 CAN buses. There was powertrain. So that was the battery, the motors, the contactors, the things that are really, really important on the vehicle. We also had 1 chassis. That was to do with suspension largely. We had 2 body CAN buses and 1 diagnostic CAN bus. Oddly, they were numbered 1 through to 6, but one of them was missing, and we never did work out why. Now, the VCM in the CID has to communicate to the outside world. Now, in most vehicles, what we have is a TCU, a telematics control unit, that provides that connectivity. And it's nearly always a separate unit to the IVI, so they're 2 separate units. In the Tesla, the cellular connectivity and the Wi-Fi were built into that CID, that central information display, just connected via USB. And they were really just dumb network connections. That cellular modem was just a connection through to the internet from the particular car. The Wi-Fi was just a USB Wi-Fi module. There wasn't really much to it in those terms. Now, this is what we normally see when we look at an IVI in a vehicle. We've got a very, very powerful Linux machine running the screen, doing the maps, doing the audio processing, the user interface, everything like that. And that will be a microprocessor-based system with external flash and external RAM. We'll then have a CAN gateway or a CAN controller. That will be a smaller microcontroller, which will have built-in flash, built-in RAM. It will have a security boundary around it, but it will be running a real-time operating system, an RTOS. And what that does is it accepts commands from that powerful Linux system. The RTOS will then receive them maybe over serial, over USB, SDIO, something like that. And it will then allow certain CAN messages to be sent outwards from the IVI. That will be quite limited. It will be filtered. If you look to the Miller-Valasek JTAG from a few years ago, they reprogrammed this CAN controller running an RTOS so that they could send arbitrary CAN messages. But it's a strong security barrier. Tesla were kind of doing the same thing. They had that powerful VCM running Linux, Ubuntu, in fact. And then they had that CAN gateway, which was running a real-time OS. And that filtered the commands that went through to the CAN buses, all 5 of them. Now, an interesting thing about the Tesla was that it doesn't use automotive Ethernet. It uses conventional Ethernet. So you can buy adapters. Now, these are quite common. It's got a FACRA connector on one end that you can plug in. There's connections. There's a diagnostic connection. You can use multiple ones of these to intercept communications between the instrument cluster and the CID. So it's just a different connector. You can plug it into a Cat5 connector on a laptop, which makes it accessible to reverse engineers. Normally, automotive Ethernet is, instead of being that traditional 4 wires, so 2 twisted pairs, it uses 1 twisted pair. It's more noise resistant like this. This is why it was developed for use in automotive situations. But on the Tesla, they went with conventional Ethernet, which surprised us. The other thing that's strange about the Tesla, I'm sure you're all aware of OBD2 connectors. So these are present on nearly all vehicles these days, or nearly all internal combustion vehicles. And they'll give you access to certain data buses on the vehicle, including at least one CAN bus that allows some diagnostics to be carried out. Now, the Tesla does have an OBD2 port on it, but it only provides power. There's no data on that connection on the Model S. We think it's just there so you can plug in dongles, so you can plug in an insurance tracker or something like that, a telematics dongle, and power it, but it doesn't have access to the CAN bus. So typically what we'd see on a modern vehicle is we'd have that OBD2 port. That OBD2 port would then connect to a CAN gateway or a body control module, and it would segregate the powertrain CAN bus, the comfort CAN bus, from that OBD2 port. You can only send a limited number of messages, diagnostic messages, from that OBD2 port. It doesn't have free access to the CAN buses. Now that means you can plug things into that, and they only present a limited risk to the vehicle. This is a CAN architecture out of a fairly typical vehicle. You can see there we've got the TIPM or CGW CAN gateway that's connected to that OBD2, data link connector, DLC is another term that people use. And that will only allow certain messages to go through to the drivetrain control, to the power control, and all these different buses. So there's that security element there, like a firewall. Oddly though, probably because the OBD2 connector on the Tesla didn't do anything, they had a diagnostic connector. Now this is hidden underneath that CID, underneath that central information display. And it's a fairly custom connector. It looks like something you'd get hidden away in a car, but it's not OBD2. But the thing is, this gives you access to all 5 CAN buses directly on the vehicle. So all 5 are presented there immediately. Now, people use OBD2 ports to perform diagnostics on their car to find out what it's doing. And Tesla owners wanted to do that same thing. They wanted to be able to access diagnostics. They wanted to find out about batteries, about speed, about power, all these different things. So what people started selling was converters that went from the Tesla diagnostic connector with all 5 CAN buses and would present those interfaces on an OBD2 connector. Now, the ones here, what they do is they present the powertrain CAN bus through to the OBD2 connector. So now you can access the powertrain CAN bus, but there isn't any filtering on it at all. So we've got access to the powertrain CAN bus, no filtering. This is starting to sound quite worrying from a security perspective. Now, if you've looked at if you've looked at OBD2 dongles at all, you'll be familiar with this, the ELM 327 or Chinese clones of the same product. These are small Bluetooth dongles. They've got a small microcontroller in them that can send a limited number of commands through to the vehicle. It's not free access through to the CAN bus, but you can do an awful lot through these. But it offers it up via Bluetooth. They're very cheap, around £10, not very much, and they're very, very common. Now, what someone realised was you could take this Diagnostics connector, convert it to OBD2, plug in an ELM 327 Bluetooth dongle, and then use your phone to perform diagnostics on the vehicle. So there's an app called Scan My Tesla that allows you to do this, and it gives you very, very detailed access to what's in the vehicle. So now we've got this situation where we've connected a Bluetooth dongle directly onto a CAN bus, and then an Android application is interacting with that. Now that would be fine if that dongle had any security on it. But the thing is, they just have a default pin of 1, 2, 3, 4 that you can't change on a lot of them. So there's no way for someone to actually secure this device. So when they're driving along, when this device is powered up, you can communicate with this OBD2 dongle and send commands onto the powertrain. That's really not a good idea. The kind of diagnostics you see, this is from when we installed it on the vehicle we had. You can see the battery voltage. It's got access to everything, the contact to the motors. And we thought, well, what would happen if you fuzzed that? Now, if anybody's ever just tried sending random arbitrary traffic onto a CAN bus of a vehicle, especially the powertrain CAN bus, you'll find that unpredictable things happen. Hopefully the car will stay safe. Hopefully it won't steer in random directions, accelerate, but you won't lose the brakes. And we did fuzz the Tesla using this. And what we found was that, it causes the car to stop. It did so safely. We didn't lose control of the steering, the brakes, the accelerator did stop working. The only thing we actually broke via this was the air conditioning. The air conditioning ceased to operate after we carried out this attack, which we did on a private closed road, just to keep things safe. But yeah, you can break a Tesla through an OBD2 dongle, which people leave connected, which is not great. So just to summarise this section, the IVI, the telematics unit, and the CAN gateway are all integrated in that one CID module. There's no conventional OBD2. There's normal Ethernet, but with weird connectors. The diagnostic connector accesses all of the CAN buses. Owners connect that CAN bus with a Bluetooth dongle, which has no security, and then you can cause the Tesla to shut down whilst it's driving through that dongle. Not great. Now let's actually tear down that CID and see what is inside that. Now, getting the CID out of the vehicle is not trivial. The first time I did it, it took me about 2 hours. It involves levering up the top of the dash. It involves removing a lot of the dash. You've got to use little airbags that you slip in to jack it up. And worse still, that massive LCD screen on the front does not have a bezel. So if you lever off the edge of that LCD screen, you will crack it. So in this picture, the LCD screen is down at the bottom, and at the top is the actual main board from the CID. Now you can start to see that that board is the same size as the LCD. It's absolutely huge. Now to break it down when we look in a bit more detail, we've got, first off, on the left-hand side here, we've got the VCM, the Visual Compute Module. It's a little socketed module that goes onto the board. We've got a big fan and a cooler on top of it. Underneath that, we've got the CAN gateway. At the top, we've got the modem and GPS. And on the lower right-hand side, we've got Wi-Fi. A lot of the other electronics in here, we've got things to deal with the display, the power, the audio amplifier. Not really security relevant. I'm not sure if you've ever seen one of these on a PCB before. It's called a TEL. And what it does is it shows you the different layers in the PCB. So it's just a little diagnostic to make sure that every layer has ended up being correctly etched. Now you can see on the front there, it goes 1, 2, 3, 4. Now on the other side, it goes all the way through to 14. That means this board has got 14 layers. 14 layers is about as many layers as you will see in devices these days. Maybe very, very small high-tech devices like iPhones and smaller phones will use more layers. But for a board of this size, 14 layers is pretty crazy. It makes reverse engineering very difficult. This is the CAN controller. So it's a Freescale SBC 56, which is PowerPC based, or Easy 200 or something like that, a derivative of PowerPC. At the top there, you can see a line of 5 chips. They are the CAN transceivers. So that's for 5 of the CAN buses. On the lower left, you can see another one. So it does have the ability to speak on 6 CAN buses, even if it doesn't actually do it. So this is a microcontroller. It's got flash, it's got RAM, all built into it. It had a big Altera Cyclone FPGA on it. Now, we're fairly sure this was used for what we call glue logic. It was for taking all of the different processors, all the different modules, and bringing them together in a configurable way. We didn't look at it in a huge depth. In terms of the cellular modem, it was a Sierra Wireless Air Prime, AR8552. It's a pretty common module used in a lot of devices. Now, the thing was, the firmware running on this was utterly stock. There was nothing reconfigured in Tesla terms. It's kind of different to a normal telematics unit. Most telematics units contain a modem and an application processor that will carry out processing. It will send CAN messages, it will provide security. This really was just acting as a modem. We've also got the GPS module on there, just the conventional U-Blocks one. Now, to look at that VCM, the visual compute module, this is the one that we took out of our car. So first off, you can see that huge heatsink. It's a very powerful processor, generates a lot of heat. So this is forced cooling on this one. Of course, to work out what's going on, we have to take that heatsink off. And then you can start to see the board in a bit more detail. So at the top there, you've got 4 chips, and you can see the squiggly traces going to them. They're called matched length traces, which means high-speed parallel signals. It's going to be RAM. So that's the DDR RAM on this device. On the left-hand side, you've got a large NAND chip that holds the bulk of the firmware. Interestingly, you can see there's a lot of unpopulated footprints. So there's chips that haven't been fitted to this particular VCM. Now, the VCM is actually made by NVIDIA. It's not made by Tesla. Now, they are fitted to other vehicles and used in other applications. We haven't found one exactly the same, though, so it could be quite custom to Tesla. Now, the particular SoC or processor on this is an NVIDIA Tegra 3. That part number doesn't seem to exist when you Google it. This is really common in automotive electronics. They'll be using processors that don't have openly available datasheets. It's probably a run made specifically for this board that isn't openly documented. But we did manage to find out quite a lot of information about it. It's ARM-based is probably the most important thing, however. Now, when we flipped it over, we found it also had another flash chip, a smaller NOR flash chip. So I think this was 64 megabytes in size. So it's a small NOR flash chip compared to the big NAND flash chip on the other side. This is used for the kernel, the bootloader, those things that need to really be high integrity. NOR flash doesn't suffer from bad blocks in the same way that NAND flash does, which is the reason we think they went for this. There's the NAND flash on the other side. Again, notice these are in BGA packages, so ball grid array, where we can't access the pins openly. However, you may notice there's a lot of test points on these boards, which allows us to access those signals without desoldering. That's the underside of the board. Kind of typical with most automotive electronics, you've got a lot of those little decoupling capacitors. Power is always considered as being dirty in a vehicle, so there's quite often strong power supply filtering to stop noise causing problems. At the top, you can see there's 4 unpopulated footprints. That's for RAM. So these devices, these VCMs, can take twice as much RAM. This one wasn't fitted with it. If you look at Tesla's other modules, some of them are populated with more RAM or more powerful processors. Now, we always do something called open source intelligence when we look at things like this. So I couldn't find any open documentation about the particular VCM used in Tesla. But what we could assume is the pinout of the connector between it and the board would be constant across all of the modules. So in the first instance, what we managed to find was a teardown of an Audi instrument cluster, I believe. And that had a board that was very similar. Not quite the same, but very similar. So we thought, well, maybe Audi's got some documentation that would help us. Maybe they've leaked something that would help us, but we didn't find anything. Of course, to build these things, you need to be able to develop for them. So NVIDIA produced development boards, development kits, so you can work with them. And there's one called the NVIDIA Jetson TX2, I think, which is this device on the right-hand side. Now, that's a development board for the VCM, for the visual compute module. Now, we thought, well, even if we can't get documentation, it's all under NDA for this particular development kit. If we buy this development kit, it will have a JTAG port on it. It will have external memory, it will have a USB, and we'll be able to reverse engineer where they go to the pins on the board, and it will gain us information. Unfortunately, they were end of life when we came to this. There was one on eBay, and I hesitated buying it because it was extremely expensive, and unfortunately someone else bought it. I haven't seen them since. Now, that massive board also had a full-size SD card socket. Now, this was connected to the CAN gateway, and it acted as file storage for that CAN gateway. Now, remember that CAN gateway is a microcontroller with built-in flash and built-in RAM. It's got limited space inside it. So this was used as storage, and we'll come on to that later. It also had a micro SD card slot. Now, oddly, to get to both of these, you had to take the CID out of the dash, which did take me 2 hours the first time. I got it down to about 15 minutes in the end. But then you also had to disassemble the CID. They weren't accessible from the outside. This just held mapping data for the navigation. Now, as I said, we didn't want to have to dismantle the car every single time, to get to this particular SD card. Because it was security relevant, what we did is we made a breakout. We cut a hole in the side of the CID, and with this flex cable, you could bring that SD card out onto the front of the dash. It meant we could unplug and replug and modify the contents of that SD card whilst the car was in operation. And we used that to try and explore the security of the updates. Now, JTAG, Joint Test Action Group, is a debug interface that's used on a lot of different microcontrollers, and it allows you access to RAM, to flash, to stop and start the processor. It's a really powerful tool for a reverse engineer. And we could see lots of white sockets on the board. So you can see 3 of them there, J10, J5. 10 pins or 20 pins shouts JTAG to a reverse engineer. It's a very, very common form factor. Now, the problem was we didn't know what the pin out was. We didn't know which pin did what on that JTAG connector. And we can obviously work out which ones are ground using a continuity tester. We can just see which ones are connected directly. But the other pins, it's an unknown. We can, and I'll talk about this later, use something called a JTAGulator to try all of the different combinations of pins. See which ones work, and then you work out which JTAG is. The problem is, a CID costs thousands and thousands of pounds. And there's a risk that if you try throwing random data at a JTAG port, you will brick devices. So we could have bricked the Tesla. We clearly didn't want to do that. So we wanted to try and work out, derive the pin out rather than guess it. They were also on the instrument cluster, so you can see a close-up there, 10 pins. There was lots and lots of them on various modules. Now, just to talk about the packaging and the ease of reverse engineering here, this is what's called LQFP, so that's low quad flat packaged, I think, yeah. So it's got all of the pins, all of the connections around the outside. From a reverse engineering perspective, this is great. I can use my multimeter to check continuity between different pins on it, see which one's a JTAG, which one's a ground, to work out how a JTAG connector is connected. The other ones we get, and this is pretty common for NAND flash, NOR flash, eMMC flash, it's what we call BGA, ball grid array. So that's what this looks like. The connectors are underneath it. So if you look at the other side of that, it's got a grid of balls on it. Now the problem is you can't access these as a reverse engineer. Now, of course, I could desolder that chip, remove it from the board, work out where the connections go, and then put it back. But when you've got one unit, when you've got one CID and breaking it costs thousands of pounds, and it'll be quite awkward to explain, you want to avoid complex operations like this. But one of the devices on the board was in LQFP. So the CAN controller, the FPGA, the VCM, everything there was BGA, ball grid array. But there was an analog to digital converter and a digital to analog, ADSP. So it does both, I believe, for doing the sound on this device. And that was in LQFP. So we had the pin out, we had a data sheet, and that meant we could use a continuity tester to work out where things went. So on the right-hand side in the red box, you're looking at the CAN controller. You can see there's no way of accessing the pins underneath it. On the left-hand side, you've got that analog devices there with the pins around the outside. That let us work out the pin out for one JTAG connector, which in turn we could use to infer that the others were the same. They're almost certainly the same. The next problem, well, what is that connector? This is a massive problem in automotive reverse engineering. We find connectors on boards and we have no idea what they're called. And there's tens of different variants of them. So I did what's natural and I went to Twitter and I said, does anybody know what this is? And within about 10 minutes, someone had come back to a link to one of the big electronic providers. Fortunately, it had to come from the US, very fiddly connector, but we managed to buy them. Now, we don't have to use connectors like this, but if you're connecting things, soldering, again, there's risk you break things. Now, the thing was we made up these connectors and then we went through every single JTAG device in the CID and the instrument cluster, and all of them had security turned on. So all of this work, and we didn't manage to gain access to anything. So takeaways from this, the CID is hugely complex. Compared to a typical IVI, telematics unit and everything, it was huge, complex, and probably very expensive to make. To buy it, to replace it was expensive, which as a reverse engineer scares me off. We only had one of them. We couldn't just buy a replacement and drop it in. There's a mixture of different levels of secrecy. That analog devices chip had an open data sheet. The CAN controller has an open data sheet, whereas the VCM made by NVIDIA, I could find very little information about. We could find the JTAG on it, but the JTAG was locked, which was unfortunate. So why do we want to recover firmware off these devices? Well, there's three different components we need to talk about here. We've got the processor. The processor is the bit that does the processing, as you'd imagine. We've got the RAM, the non-volatile storage. Now, again, as a reverse engineer, when we're talking about modern microcontrollers with external RAM, it's normally something called DDR, dual data rate or double data rate, and it will operate at 600 megahertz, 800 megahertz with tens of signals going into it. We can't really intercept that or sniff it or work out what's going on. It's very difficult. However, when you look at the flash memory on a device, that's where the firmware is stored, the non-volatile storage. It's like a hard drive. Now, the great thing here is quite often these have a very limited number of signals going to them, and we can read them very slowly. We don't have to mess about with very high-speed signals. So recovering that flash allows us to reverse engineer devices. So just to look at, this is a IP camera. This is a microprocessor-based device. So it's got the processor as one unit there, similar to the Integra with a big steel casing or aluminium heat spreader on top of it. We've got the RAM at the bottom there, so there's two chips on this one. Again, you see those squiggly traces. This is always a sign of high-speed parallel signals. And then on the right-hand side, you've got the flash. They're external packages. As a reverse engineer, that means I can desolder that flash. It means I can read it off the board. It makes it easier to attack. So for a microprocessor, the security boundary is around the processor, but the flash and the RAM are external. You also get what we call microcontrollers. So that's got a processor, the RAM, and the flash all contained within the semiconductor package. Of course, that means I can't intercept the signals easily going between the flash and the processor. So that security boundary is set all the way around the outside. So why do we want to do this? Well, imagine I've got a telematics unit here, and it's got USB, CAN, Wi-Fi, different interfaces. But if we treat it as a black box, we've only got a limited amount of knowledge about what it's doing. If we open that box up, we get access to the flash. So the firmware could contain the binaries that run it, which might have vulnerabilities in them. It could contain any shared cryptographic keys that are across all of the devices. We've got UARTs or serial consoles as well on these things. So quite often that will allow you access to either the bootloader or the operating system directly. We've got the RAM. The RAM, although it's hard to access at the physical interface level, once we've compromised the rest of the device, if we can read the RAM, it can be really helpful. It can contain things like decrypted data, secret keys, temporal information that we want to recover. And lastly, we've got JTAG. Now, JTAG itself allows access to all of these other components, so it can be very helpful for us. Now, in terms of getting hold of the firmware, I'm a lazy person fundamentally. And we want to take the easiest route to start with. So the easiest way to get hold of firmware for a lot of devices is to simply download it. And that's common for lots of IVIs. You can download the firmware updates online and examine them. You don't even need the IVI to be able to access it. The next way, you can intercept those firmware updates, so we can instrument the device. So with the Tesla, what we could try to do was see if we could intercept the Wi-Fi and see if you could get access to that firmware. Sometimes it leaks. That's pretty common on a lot of devices. Someone will commit their code to GitHub by mistake, and then it will sit there and we'll find it. We then move on to the actual hardware attacks. The serial console on a device, a chip-on memory read. So chip-on is when we read the flash chip when it's still mounted in the device. Try to find JTAG and read out that way. Chip-off, where you desolder the flash memory and read it off the device. And finally, advanced methods like decapping chips and side channel attacks. But we want to keep things simple and easy, generally. One other problem we find is sometimes updates can be complete. They'll contain the bootloader, the operating system, the application. It gives us that full picture, that full understanding. So when we're downloading or intercepting updates, we hope to get the whole thing, but sometimes we don't. It's quite common to just get the application. So you'll miss the operating system and the bootloader. But since OTA updates have become more and more common on vehicles where we've got constrained bandwidth, people don't want to spend money shifting data they don't need. We get what are called delta updates. And this is what the Tesla did. It only updates the smallest parts that it needs to, just the changes. And rebuilding a whole firmware image from that can be really, really challenging. In terms of the way that firmware is stored on devices, this is called a SOIC-8, Small Outline Integrated Circuit 8-pin chip. And it's SPI flash. The great thing about this is we only need to connect 4 signal wires to be able to read this. So from my perspective, these are trivial to work with. Those pins, although I know this is a magnified image, the pins are quite a long way apart. We move on to BGA. Now, this is a NAND chip, but it's got a serial interface going to it. So we don't have to intercept tens of signals going to it. So we could desolder that chip, or we could just try and find where those signals go and interact with them. Probably the most awkward one from a chip on, reading it on the board, is what we call parallel NAND flash. You can see how many pins this has got. Connecting to all of them on a board is obviously challenging. The thing is, they're very easy to desolder off boards and read off the device. To connect those little 8-pin ones, we use these clips. These are great. You just clip it on, it will connect to all 8 pins, you've got access to them. And then with that, you can use a logic analyzer to see what's being read and written, or you can actively interact with that chip and read the firmware back. So what is JTAG? Well, it's an electrical interface. You've got 5 signals there: TDI, data in; TDO, data out; TMS, which changes the state; TCK, clock; and TRST, reset. Within the processor, you've got something called a JTAG controller, and that allows you to interact with the flash, the CPU, and the RAM, as well as do something called a boundary scan. Boundary scans are what JTAG was initially used to do. It was to interact with individual pins on devices. Now, we find these interfaces on lots of things. This is from a router, and you can see conveniently this one's labeled JTAG. And this is a very common form factor. So this one, oddly, is missing 2 of the pins at the end. I don't know why they only fitted it like that. You needed to manually put them on to interact with one of the chips on here. But 10-pin and 20-pin connectors are so often JTAG. This is the kind of situation you end up with. So here I am testing a small ECU, which has JTAG. I've found where the pins go on it, and now I've connected it to that black box on the left-hand side, which is called a Sega J-Link. It's a JTAG interface. And that let me recover the flash memory from this device so I could analyze it and work out what was going on. I mentioned something called the JTAGulator that just tries all of the different combinations of JTAG pins. Now, this is a special dedicated device. I think it's got 22 channels on it, so you can pick 22 points on a board and connect to it, and it will try every permutation of the pins, TDI, TDO, and so on, and see if it gets any expected responses back. The thing is, you do risk damaging boards. Every now and then you'll send something that will cause a board to be damaged. but it's another tool in the arsenal. You end up in these situations where you'll find connectors on boards that are unpopulated, or traces or test points. And we spend a lot of our time soldering very, very fine wires onto devices. Now, if you're not from the UK, you probably don't know how big a 5p is, but the 5p coin there is the smallest coin we have. It's pretty tiny. So you can see the kind of scale we're working at here. But we use this to try and find out where signals are going on a device. This is another board, and on the left-hand side there, you can see we've got a high-density connector. So these are used quite often to carry daughter boards and things like that, high-speed signals. But the distance between each connection is 0.5 of a millimetre. I think that one there's got 64 pins. So that'd be 64 wires being soldered on that finely. I'm not going to succeed. I'm going to break it trying to do that. So what we do is we make breakout boards. So this is a custom board we made that plugs into that connector and gives us access on a much larger 2.54mm pin pitch connector. So we can find JTAG, we can find serial ports and interact with the device. The next thing we quite often do is we use a toaster oven. This is an actual toaster oven, and we put the device into the toaster oven. Why are we doing that? Well, we want to melt all of the solder on it so we can take all of the components off. We didn't do this with the Tesla. Firstly, it wouldn't fit, the CID would not fit in a toaster oven, and it was just too expensive. But this is a technique we've used on a lot of IVIs. So we put it in the oven, we heat it up, and then when it's hot enough, we hit it hard on the desk, and all of the components just fall off. And we're left with a largely bare printed circuit board. Here, I'm trying to clean that up using a soldering iron to get the worst of the solder off. And what I've done here is scan in that board. So now you can see here, we've got the points that you could solder to. The green layer, the solder mask, the thing that stops solder sticking to the copper tracks. And then underneath that, you've got all of those copper tracks. Remember I said how the Tesla circuit board had 14 layers? It's quite common to find devices with 4, 8, 16 layers. And we might want to look down into those middle layers. So what we do is we sand off the solder mask and then we sand through the layers, going through them gradually. So this is after I've taken the solder mask off. So I've rubbed it on a piece of glass with abrasive on it. And now you can see all of those traces going about. And this is a really rich tool to reverse engineer. I can now use paint. I mean it, like normal paint. And you can click on a contact on one of the chips and it will fill in that trace. So you can see where it goes to on the other side of the board. So here we've got the blue traces, squiggly, it's RAM. We've got red traces going through to an analog to digital converter. The yellow traces are HDMI. We can trace them all back to pins on the main processor. So when you zoom in, you can see all of the balls that would connect the underside of that chip. It's a really powerful tool to work out where JTAG goes to reverse engineer devices. Another tool we can use is X-ray. It can be quite frustrating at times. This is a Quectel modem, I believe, out of a telematics unit. It's a 16-layer board. So for the size it is, you can see the density of the chips that have been taken off there. Reverse engineering this would be very, very challenging. But you can see those middle layers with an X-ray. So this is looking straight through a device. So you can see all those overlapping traces. Now again, it's all providing clues. They're tools in our arsenal to reverse engineer things. In terms of chip off firmware reads, so taking a flash memory chip off a device, we tend to use hot air. So you use hot air to melt the solder on the device, you lift it off, and then we've got a data man. There's a different company in the US that's much more common. This is called a universal programmer. And with these adapters, you can read pretty much any memory chip. The problem is the adapters cost £400–500 sometimes. So every different type of memory chip we come across ends up with another adapter. Here we're actually reading the firmware off a smart fridge. You know, we couldn't download it, we couldn't intercept it, so we took the chip off to read it. Right at the beginning, you remember that I said the instrument cluster had a VCM in it, a visual compute module. Now the thing was, I could buy clusters online for about £100. They weren't working, the screen was smashed, they'd been damaged, but much cheaper than a CID. So we bought some to look at, to try and reverse engineer them, because you've got that same VCM, that same connector. It's passively cooled on the Instrument Plus. There's no forced air on this one. It's got a different NAND flash architecture. Oddly, you can see this one, although it's also got unpopulated RAM slots on it, they're all on the same side. So there were differences, but still not really enough. Again, we went through this board trying to find JTAG, and we did. Unfortunately, on the VCM, it was locked. You can again see with my slightly dodgy soldering here, the amount of wires we have to connect to these devices to try and find interfaces like this. They're speed bumps in reverse engineering. They're not strong security controls, but certainly it did slow me down. Now, one of the other things we get, and this is what stopped us getting the firmware off all of the different microcontrollers and microprocessors in the Tesla, is what we call code readout protection, or CRP. This is what stops you reading out flash memory through JTAG. So we've got that barrier, that red line around the flash, the CPU and the RAM. Code readout protection is stopping us being able to access that. Now, JTAG is really just an electrical interface. It's got this state machine that allows you to write and read certain registers, but JTAG doesn't really necessarily allow you to read flash or RAM or anything like that. It's kind of implemented different ways by different chip manufacturers. So almost always you get something called an ID code read. That means you can just find out what type of chip it is. Now, we managed to get that back off a couple of devices in the CID. You also get something called bypass that just checks you can shift data and control those pins around the outside using boundary scan. But the non-standard stuff is accessing the CPU, the RAM and the flash, but also how JTAG security is implemented. Now, this can be a massive upside or a downside to a reverse engineer. Sometimes JTAG security is really strong. You'll need to provide a long password, a long ID or something to be able to access devices. Other times they might have security, but there's easy ways for us to bypass that security and get access to the code. Now, we found that the automotive industry very commonly is very reliant on JTAG security. Once you've broken through that layer, once you've recovered the firmware, things like shared keys are quite common. So I'll take you through a few of these attacks. First off is hidden or forgotten bootloader options. So the bootloader is the first stage of code that runs on a device, and it quite often decides what happens. It decides whether you're going to boot from NOR flash or NAND flash, whether you're going to take a new firmware update through the USB port or something like that. I can't show you what the device is, but on the left-hand side you'll recognise I've got my Sega J-Link connected to this device. We'd found JTAG on it. However, it was actually SWD, which is a variant really, a 2-wire variant. It said the ECRP, the electronic enhanced code readout protection value, said that SWD access is disabled. To restore SWD access, you can wipe the flash in mass arrays, but we don't want to wipe the flash because we want to get hold of the flash via SWD. So we didn't want to mass erase it, but we wanted to work out a way of getting onto this device. So we looked to the data sheet, and this particular chip, an LCP 16 something or other, has what are called ISP, in-system programming modes. Now, the one it was in by default, it boots from flash. So the bootloader will go to flash and it will run the code that's expecting. But you could change pin values and you can make it turn into a mass storage device and then program it through USB. So we thought, could we easily change what happens here and re-enable SWD? So what we did was, this was a white box full knowledge test. We had a schematic and we saw those ISP pins were PIO 4, 5 and 6. We looked at the schematic and we saw that there were 3 lines going to the display on this device. So it had an LCD display. We then looked to another part of the datasheet and we saw it had test points for those 3 signals. So there's a big group of test points here. We could access those signals, and simply by connecting resistors to pull them high or low, we managed to put this device into USB mass storage mode. And it conveniently shows up as a device called CRP disabled. So it's explicitly telling you code readout protection is disabled. We read back the firmware through that mass storage device. Now, this is where the real vulnerability in this device is. To turn on that enhanced code readout protection or not is actually stored in the flash. So if you manage to get hold of the flash, if you manage to program it, you can turn SWD, you can turn code readout protection on or off. It's a bit of a strange way of doing it. Normally, people would use what are called fuses, things you blow one time. This does have something called OTP, one-time programmable, same as fuses, that you could set that override it. But it wasn't in the main data sheet. It was hard to find. So we read it back and we saw there was this value. We thought, well, let's change it from SWD disabled to SWD enabled. We put it back on via USB. And then at that point, we had full SWD or JTAG access to the device. So we could read the RAM, we could read the flash, we could stop and start the processor. It was complete understanding of how that device worked. The rest of it was brilliantly secure. It was just this little omission that someone didn't realize you could do this. The next one is a more generic attack. It's called the Heart of Darkness attack from a paper that was actually to do with bypassing security controls in RFID access. Now, those readers they looked at were based on a PIC microcontroller. So they're those small 8-bit, 12-bit microcontrollers, a little bit older, not quite as common as they were. What these do is they divide their flash memory that holds the firmware into blocks, and you can erase an individual block and leave the other ones intact. So this is key. I can erase the boot block and leave the firmware. I can erase block 0 and leave the boot block in place. So you don't have to do a mass erase where you wipe all of the flash of the device. So we've got the standard situation. Someone's enabled code readout protection. We can't read anything on that device. But what we can do, an attacker, we can erase the boot block. So it will have a bootloader, something basic in it. We'll erase that, so we'll turn the code readout protection off. We'll then get a very, very simple bit of code. And all that bit of code will do is it will loop through the locked flash areas and output them through the serial console. So it's just reading the memory and then providing it through a serial console. We program that into the boot block of the device, and then it loops through and we've got access to the firmware. Now, of course, you've erased the bootloader and you might want to gain access to that. And we can, of course, change this. So the first time we erase the boot block, do the dump, and it goes through block 0 through to 3. The next time, what we can do is we can wipe block 0 through to 3 and just program the dumper into the end that just dumps the boot block. That means we've destroyed 2 devices to get an entire firmware image. But that cost may not be big enough for someone to worry about. Loads and loads of silicon vendors recognize this. This is from Scilab's EM3598, which is a common RF chip. And it says that if read protection is active, then write protection should also be active because it stops you carrying out this attack. But we still find this frequently. The last one's more like implementation bug that's been found in a lot of ARM Cortex processors, particularly the STM32. So there's a bit of research by an institute in Germany. It's got 3 or 4 different attacks in this paper. It's a great paper. So the situation here is we've got our JTAG controller, and when it's unlocked, we've got access to the flash, the CPU, and the RAM. Now, when you lock this particular device, it stops you accessing the flash and the RAM. So we can't read out the firmware. We can't gain access to the secrets in the RAM. But there's no detail on how that JTAG controller works. It is literally a black box. No one really understands it. No one knows where it comes from. Now, what was actually found here was that you've got 2 sides here. On the left-hand side, us interacting via JTAG. On the right-hand side is what's going on the inside of the chip. So we initialize the JTAG. We read that ID code, that thing that tells us what the chip is. It's just to make sure we know it's the right chip. We do some messing around. We initialize some registers. We do some more messing around, making sure everything's working properly, the speed's correct and things like that. A little bit more messing about. At this point, the inside of the device has locked the flash. It's stopping the flash being read out. So now that the flash is locked, we try reading the flash, we get denied. We can't read the flash. So it hasn't worked. So that's how that security works. But what we thought, or what these guys thought, was, well, what happens if you just get rid of all of that messing about? What happens if you just forget about that? And it turns out, in this case, you don't have to do any of that messing about. And you end up with a race condition, where you're able to read the flash because the internals of the processor haven't read it. Now the thing is, the second you read that flash, it locks the flash. It means you can only recover 1 byte of firmware at a time. So you read, or 1 address worth of firmware. So it's 4 bytes in this case. So it's slow. You have to reset the device, read the next byte, reset the device, read the next byte. So you reset the system, initialize debug, read the flash, reset the system, and go round and round in this loop. It's very time consuming. So how do we automate that? Well, instead of using a normal debugger, we use an attacking system. So it's interacting using SWD JTAG, and then we've also got control of the reset, so we can power cycle the device. Now we could use a laptop to do this, but the problem is laptops with USB, the timing's not accurate, there's latency there. So what people tend to do is they use another microcontroller that's running a small firmware that allows us to carry out these attacks. This is the picture from their paper. So you can see we've got 2 boards exactly the same. One of them's interacting with the other one to carry out this multiple reset, read a byte, multiple reset, read a byte, and you get the whole firmware off the device. This is just a few different attacks that we can carry out. There's so many different ones of them. So why does it need to be secret? Well, you may have heard this. This is Kirchhoff's principle, not Kirchhoff's, which is the current one. A crypto system should be secure, even if everything about the system, except the key, is public knowledge. Now that might hold true. That really means that, our cryptography we use, the only thing we should care about keeping secret is the key. The algorithms, the programs, the code that runs it can be open, and that shouldn't weaken it. But the problem is that every now and then you do introduce vulnerabilities into your code. It can be a viable layer of security. So you've probably heard of security through obscurity. This is the Wikipedia definition. Security through obscurity is the reliance on the secrecy of the design or the implementation to provide a security control. So the problem here is that I've found a lot in automotive, people rely on that JTAG code readout protection to hide secrets inside those devices. Once you've pulled them out, bad things happen. Someone else said security by obscurity. So that's only relying on obscurity is bad, but security with obscurity isn't. So layering obscurity around your device can be a valid control. Why is it particularly important with cars? Well, cars have got to make real-time decisions, which means they've got to do local processing. With the advent of ADAS, there's a lot of intellectual property on cars. You've got LiDAR, you've got cameras, you've got the vision processors, all of these different devices running code that you probably want to protect. So sometimes you do want to stop people stealing that. But someone with enough time and money can probably get code off a device. Every now and then, there's a symmetric device-wide key, something like a bootloader key that protects firmware updates. If we can recover that off one device, we end up with what we call a break once, run everywhere attack, a BOR attack. We can just put a lot of effort into one device and get something high value that we can use off others. Again, we find this a lot. The firmware will contain secrets that impact multiple devices. In certain situations as well, there will be information on a device that we care about ourselves. Say VPN keys off a Tesla, which we'll come on to. This is an excerpt from a microchip datasheet talking about code readout protection. Microchip believes that its family of products is one of the most secure families of its kind on the market today when used in the intended manner and under normal conditions. I'm a hacker. I don't care about normal conditions or the intended manner. It's my job to use things outside the intended manner. There are dishonest and possibly illegal methods used to breach the code protection feature. I mean, again, it doesn't really matter if it's dishonest. If I can use it against the device and recover the firmware. These methods require using the microchip products in a manner outside the operating specifications. Again, this is a great thing I have. If I need to power a board at 2.4 volts so that I can exploit some vulnerability, it wouldn't work in a car, but it works on my bench. That's all I need. They do turn it around and they say that code protection does not mean that you're guaranteeing the product's unbreakable. So you've always got to bear this in mind when looking at your devices. Now moving on, there's 2 different types of analysis we do when we've recovered a firmware, and we did this with the Tesla quite a lot. We've got static analysis. So that's when you pull the firmware off a device and you analyze it without running it. It's got advantages. It means you can look at all of the firmware, hidden bits, debug functionality and things like that. But it can take a lot of time to do that. And you're also relying on inference. You're guessing at what it does. The other one's dynamic, where you actually run the code. That can leave code paths uncovered. If you need a secret key to unlock something or something like that, you're not going to see it through dynamic analysis. But it's often fast, and you can actually demonstrate vulnerabilities. One of the first things we do when we pull any firmware off a device is we run a tool called file on it. And what file does, it's a Linux utility, and it just has a guess at what's in that file. Now here I've run it on a file from a camera. It tells us it's an ARM executable. It tells us it's dynamically linked, which means it relies on external libraries. But it tells us, importantly, it's not stripped. Stripping's removing the debug symbols from a binary. If you leave those debug symbols in a binary, it gives you names and clues. The other thing we often run is just a tool called strings. Strings allows us to extract ASCII strings. It just guesses again. If you get 4 or 8 bytes of consecutive ASCII, it will dump it. So again, you can see quite quickly from a particular binary, this has told us it probably serves HTML, because we can see HTML there. In terms of ease of reverse engineering, again, I'm lazy. I want to go for the easy option here. From a reverse engineering perspective, the easiest by far are shell scripts, bash scripts. We can open them in a text editor and read them. They'll have comments in them a lot of the time. We've then got interpreted languages like Python and PHP. Again, you can just read those. Java and C# are interesting. You can turn them back into human readable code, because they end up with an intermediate bytecode where we've got all the variable names and function names preserved. Again, this is a powerful tool. We then move on to C and C++, which get a lot harder. We rely on disassembly, turning it back into assembly instructions most of the time. So disassembly, the tools we use are IDA and JIDRA. They take that compiled binary and they turn it back into assembly instructions. So hopefully if you've got the right skills, you can understand it. The kind of output you get is something like this. Now this was a binary that wasn't stripped, so we've got all of the function names. You can see we've got set web service mode, append data, prepare body, giving us clues. We end up with the assembly instructions, and we can see a reference to a string there. There's more clues. There's still a lot of inference. You look to that on the right hand side there, it's going to take time to work through that to work out what a binary does. Strings are such a massive clue here. When a device interacts with people, when a device interacts with internet servers, it tends to have lots of strings in it. HTML is full of strings, XML is full of strings, it's verbose. When you move to things like CAN gateways though, things that only receive CAN messages and send them out, there's very infrequently ASCII in it. And that means that reverse engineering those smaller microcontrollers like CAN gateways and smaller ECUs in a vehicle can be a lot more time consuming, but they tend to be less security relevant. We can also decompile code. So instead of turning that back into assembly, we have a guess. A tool will have a guess at turning it into C. It works sometimes. In this situation here, we can see we're putting and printing certain strings. It kind of makes sense, but a lot of the time, it doesn't really help us. Another challenge we have when working with Automotive is that we need to emulate the code we're running. We had to do this with the Tesla. We tend to be Intel based, our laptops are Intel based, but ARM is used in infotainment system, MIPS is used in some ECUs. In Automotive, the RH850 and PowerPC is absolutely everywhere in smaller ECUs. It means we can't run the code directly, we've got to pretend to be one of those processors. Sometimes that's easy to do with a single binary. You can take one binary off a device and run it. So I'm running a binary here, it's an ARM binary, and it runs on my Intel laptop. And we could do this with the Tesla. Sometimes you need to run the whole operating system. So you take the entire flash image and try and run it. The problem is that your emulated system won't have all of that hardware around the edge. It won't have that CAN controller. It won't have that modem. And quite often it can be really, really hard to get that going. So what we find the best approach is to use static and dynamic analysis hand in hand. You do some static analysis to work out what's going on. You use dynamic analysis to test that hypothesis. And you keep on going round and round until you discover more and more about how something operates. So now onto the Tesla and what we learn. we've got the firmware off of it. The firmware is read by desoldering the flash chip and reading it out. It was the simplest way of doing this. A few minutes ago, I said the easiest way to reverse engineer, the laziest way, a shell script. And this was the brilliant thing about the Tesla CID. It's running Ubuntu. And I did a search for shell scripts. And you can see here, we've got a shell script called car is parked. That literally is a shell script, a bash script, that checks to see if the parking brake's on. It's got other ones like get Wi-Fi MAC address, gateway, put car to sleep. These are all shell scripts I can read easily that are interacting with the vehicle. Now, for maybe about half of these, they were deprecated. They were no longer used, but they were still on the device. They'd been replaced with binaries, but the same functionality was implemented in a shell script. I'm lazy. I'd much rather read a shell script and work out what's going on than go for the binary. Now, the one that we quite quickly found was called do firmware handshake. And you remember I said comments in there. This was a heavily commented script. I didn't even really have to read the code to mostly understand what was going on. And this actually gave us a really good understanding of how the Tesla updated its firmware. Things had changed since this shell script. They'd moved into a binary, but this was a massive clue to what they were doing. We did find something interesting in there. So this is an array of VIN numbers, vehicle identification numbers, and there was a hard-coded list of them in the USB update. So you could update this by plugging a USB stick into it. And if you're one of these VIN numbers, including those two strange ones, Rob Model S at the bottom, you got certain features unlocked on the vehicle. But that was just in a bash script. Now, the file that quickly drew our interest was called CID Updater. And we ran that file tool on it. And it told us various things. ARM. We really like ARM because there's tools available for it. It's really well understood. Compared to RH850 and PowerPC, it's so much easier going for us. It's statically linked. That means it doesn't rely on any external libraries. Everything that it needs to run, practically, is in the code blob here. That makes it easier for us to emulate. And we did. We could run this on our own laptops and work out how it's working. Lastly, it wasn't stripped. That meant that all of those function names were contained within there, giving us massive clues to how it worked. Just to give you a clue, just an idea of the difference between a stripped and an unstripped binary. This is an unstripped binary. So you can see I've got all of these functions here. LD2 blink, probably blinks an LED. System clock config, UART. We've got all of these names. I don't even have to look at the code to work out what's going on. We look at LD2 blink and we've got variable names. We can see it's saying blink speed. We probably know that this is changing the speed and LEDs blink here. Makes it much easier to work with. When we strip it, we lose the names of those functions. IDA just calls them sub-memory address. We lose the names of those variables. It makes our life much more difficult. Now, Tesla really slipped up, I think, by leaving debug symbols in their binaries. It made our life much easier. Now, the first thing that we noticed when reverse engineering this binary is it had this concept of what they call personalities. The CID updater was actually on the instrument cluster as well. And it just checked to see what you named the file when you ran it. So if it was called CID Updater, its personality was CID Updater. If you called it IC Updater, it turned into the Instrument Cluster Updater. We also had other ones, GWX for Gateway Transfer. That was used to communicate with the CAN gateway. The one that I never really worked out was SM Updater. We found a few strings that said site master. So we're not sure that there was a concept of a site master, maybe something in the Tesla factory that allowed you to program the firmware when it was there. So to kind of break this down into how the whole thing was brought together, we've got the CID in the middle here. We've got the CID updater, which is one personality. That's the one that connects to the cloud. We've got gateway transfer. That's the one that connects through to the CAN gateway. And we've got IC updater. So these three are actually all the same executable, just with different personalities. We could trace through the code and see how they were behaving differently when they're in these different personalities. Now, I mentioned that we could emulate this. So here I am emulating IC updater. So I've renamed that file IC, Instrument Cluster Updater, and I've just run it. It's ARM code running on my machine. And we're getting debug logs coming out of there. Now, there's interesting things there. You could see it saying creating command listener for personality IC updater, creating HTTP listener. So the way that the instrument cluster and the CID communicate are using a web API. So it can just send and receive commands from one to the other. And there's a big long list of commands. So we've got things like debug, HTTP get. You could get files, you could set a heartbeat going, you could read and write memory, you could install things. There was all of these different commands getting sent from one to the other. There wasn't any security on that. So if you're on that network, if you're on the network between the instrument cluster and the CID, you could intercept these and mess about with them. So here's us. What we're doing here is we're connecting through to that command port on the IC updater, and we're giving it the command serve start /etc password. Then we're just running a wget, just a normal command to get a web page, and we recover that password file. So again, this was a way of us connecting to the instrument cluster, connecting to the CID when it was in a certain state, and we could actually read and write arbitrary files on that device. There was no password, no security. You could also run status. So we're running a status command here, and you can see this verbose information. There was a few interesting things here. Bear in mind that I'm running this on my laptop, and it doesn't have all of the hardware that surrounds it that it needs. You can see we've got bank A and bank B. The Tesla has dual banked firmware, so you've got an A bank and a B bank, so you can update B whilst A is running, toggle over to it, and then get reduced update times. You've got the concept of a recovery partition as well. There was some attempts at security in some places that I didn't really understand. One of the things that it did was it hashed itself. So when I ran IC Updater, it performed a SHA-512 hash of itself, and then in certain communications, it would send the first few bytes of that through to the other end. If it didn't match what the other end was expecting, if it was a different version or it had been modified, the other end would say, no, I'm not going to speak with you. The weird thing was, though, because this was all over HTTP or plain text, you could just modify the binary and send a different value. Not particularly strong integrity protection. You could, of course, actually put these into development mode anyway, which bypassed a lot of these security checks. So it bypassed signature checks. It made it a lot easier to work with. Now, I built these massive sequence diagrams to show how these things work. And I'm going to go through these step by step to show you how the Tesla first off downloads firmware. So the first thing off is the VPN connection. It established a VPN connection outbound. So we've got that CID updater communicating with the cloud. It needs to download and get firmware updates. And it does this over a VPN. Now, each vehicle had its own VPN certificate. It was identified by the VIN number of the vehicle. So you can see the VIN number of the vehicle there. Each one was different, but you could read it off the flash memory of an individual car and then use it on your own laptop to connect to the Tesla VPN. So the idea was they secured all of their communications with a VPN. Your VIN number keyed identified that certificate. But the problem was that once you were on that VPN and you started making requests through to a web server using your VIN number like that, there's no strong link between the VPN and your VIN number. So an attacker could come along, take the VPN certificate off Tesla A, change it to the VIN number of Tesla B, and make web requests using that. So there was no link between the VPN and all of these other requests being made. Of course, VIN numbers are shown on the dashboard or B pillar of a car. You know, they're not exactly hard to get. You could enumerate vehicles. There's not much entropy. There's not much randomness in a VIN number. So you could just make requests through to Tesla endpoints that they call the mother load and find out details about the vehicle. So you can find out when it was born. You can find out what's called the vehicle hardware configuration string. What hardware is in that vehicle. This vehicle had been hammered, written off. This was a written off car that we are looking at here. One other thing we often find with telematics units and things like this are problems with the configuration of the APN, or access point name. This is the bridge between the cellular world and the IP world. So quite often we get what are called public APNs. So your telematics unit will communicate with the public APN and it will just go out to the internet. But it's also common to get what we call private APNs. And that would be an APN dedicated to a particular telematics provider, a particular car manufacturer. and that will have a VPN going through to a private network. So as long as you've got access to that APN, probably using a SIM card and some credentials, you've got access to that private network. Of course, SIM cards can be removed from devices. Now, the Tesla, oddly, just relies on completely public internet. The Tesla we had just had an O2 SIM card in it and was connecting through to the internet. But on other telematics unit, we've pulled the SIM card out, and what we've done is we've used that to access a private APN and then access devices on a private network that we shouldn't do. So the standard pattern is GSM or 3G or 4G, LTE, HSDPA, go out to that APN or similar. That VPN connection is established, and then you've got access to that private endpoint. So the telematics client might be meaning to go through to a telematics server. But again, if I compromise that TCU, if I gain access to that APN, I might be able to gain access to something like a domain controller. Now, Tesla set up a load of different network routes when you connected to their VPN, and you could actually port scan things and explore it. There wasn't a huge amount there, though. The next thing was getting the details of the vehicle. I mentioned that vehicle hardware configuration string. And what happens there is the CID goes to the gateway and it says what hardware is in this car. And it does that using the updater in the gateway transfer mode. It connects via IP through to the gateway and it will read the configuration. That's things like what battery have you got, what motor have you got, are you left-hand drive, right-hand drive. Once again, gateway transfer was a big binary, but there was an older version that was written as a Perl script. We could reverse engineer that far more quickly. It had comments in it, had verbose help, so we could work out it was a UDP protocol with very little security. So it read a file called internal.dat back from the gateway onto itself, and it formed this vehicle hardware configuration string. Then the next step was what was called the handshake. Data, including the vehicle hardware configuration string and things like that, the VIN number was sent through to a Tesla server. So it sent all of that data through saying, I want a firmware update. And then the other end said, yeah, here's a firmware update for you. So at the top there, we've got the firmware server that we go to, only accessible via the VPN. The middle's that disassembled code where we're saying, look, this is our vehicle, this is who we are. And then we get the handshake response down at the bottom. Let's break down those individual components there, the interesting ones. So at the top, first off, you'll notice there's a URL to download the firmware. First off, right at the beginning, HTTP. It's not HTTPS, it's HTTP. Now, this wasn't actually downloaded over the VPN. It was publicly accessible on that server. Now, it was an individual URL for that vehicle. So it was generated on demand from what you just requested. It expired in 2 weeks as well. But that meant you could just download the firmware freely from a computer after intercepting this. The next thing is you'll notice there's a crypto key. Now, I presume because they were transferring this over HTTP, no TLS, no SSL, no security, they wanted to encrypt it. So there's a cryptographic key provided over the VPN. Finally, there was a firmware download MD5, so a hash representing that firmware. Again, that was transmitted over the VPN. That means it was securely transmitted, and that meant you could check the integrity of that firmware that was downloaded. So the next thing is it goes through and it requests and downloads that firmware. So just to show that in a bit more detail, over the VPN, we make a request for the firmware. We get an MD5 hash, a URL, and the encryption key. It's transmitted securely. No one should be able to tamper with that. Then the encrypted firmware is downloaded over HTTP. So someone could tamper with it, someone could mess with it, but that would be detected when they check the integrity later. It does still mean you can download 8 gigabytes of firmware update. 1 byte in it will be flipped and it will fail that integrity check and it will all have to start again. I don't know why they didn't use TLS. Now, there were 3 different paths that the firmware could then be installed onto the CID. The first one was tar.gzip files. It would unpack them, there'd be an install.sh script in there, it would run them. We never saw that used. I think it's deprecated. There's one called bsdiff, which is a kind of existing Linux patching mechanism. Again, we didn't see this used. But the one that was used was Harman Redbend. So this is dedicated OTA diff patching. So you send small diffs, they get applied to the device. Now, I have to say, trying to reverse engineer this, it was built into the updater binary, which meant we had symbols, but the code was just incredibly dense. I think, there's a lot of compression, there's a lot of trying to work out how to apply diffs to be as efficient as possible. But we did work out this was something called red bend VRM. It seemed quite efficient, but it didn't seem to apply any particular security in and of itself. When we looked at how it worked, we had this concept of A and B. So we had a kernel A and B, we had bootloaders, which were called primary and recovery, and then finally we had online and offline partitions. The idea here was that when you downloaded an update, it was applied to the offline partition, and then you'd flip over. So you'd move the online to the offline, which meant that you had a fallback to go to. It meant you could carry out updates without interrupting the vehicle. So you've got that identity, the VIN and the hardware stored on the gateway, which is pulled back to the CID. Updates are generated for each vehicle. So I could actually change the hardware parameters and get a different update for the same vehicle. So it didn't actually seem to validate that the vehicle was as expected, which I was surprised by. Downloaded over HTTP, so no encryption. The integrity and the confidentiality were done via custom encryption, which again seemed a bit strange. Why not just use something widely known? The red bend system was used to actually install the update, and it was dual banked for reliability and speed. So we learned quite a lot about how it downloads updates. It was a bit unconventional, but kind of maybe what we were expecting. But the thing that the Tesla was doing that was maybe of more interest was actually updating all the individual ECUs around the vehicle. So it wasn't just updating the CID, it was updating smaller ECUs. So we looked into how this works. Again, a massive sequence diagram to show you how this all works. So the first thing that happened was the CID transferred something called noboot.image and release.tgz to the gateway. Now to show you that on this diagram, it used gateway transfer to move it across to the CAN gateway. That was a microcontroller with built-in flash. It didn't have nearly enough room to store the firmware of 30 or 40 ECUs. So it put them onto that big SD card. That was where the firmware updates were stored. Now you remember I showed you this picture earlier. We extended that SD card out so we could access it whilst the vehicle was in operation. And then you open yourself up to a class of vulnerability called top2, time of check to time of use. It was transferring the CID files onto this SD card, and then the SD card was being used to update all of the ECUs. So what were those files? Well, we had noboot.image. That was actually a firmware for the CAN gateway itself. It was a dedicated firmware that was used to carry out updates. It also had a big tar.gzip called release.tgz. That contained the individual files. Now the interesting thing here is it sends that noboot.image, which then the CAN gateway boots into. At that point, that CAN gateway ceases to operate as a CAN gateway. It's a firmware updater. That means that whilst this process was happening on the Model S, the vehicle did not work. And we're talking really didn't work. Nothing, it was hazard lights, and that was about it. It had to be parked, but there was no functionality. So I'm just showing you the contents of that SD card there. We could just unplug it and read it at will. Now the thing was that noboot.image was actually checking the signatures of each one of these firmware files. So it was going through and checking that they matched as expected. They were signed by Tesla. So this meant that even if we managed to tamper with the SD card, we didn't manage to change what was going to the ECUs. So it unpacks that release.tgz into hex files, conventional Intel hex files, and a manifest file. So you can see here we've got all the different ECUs around the vehicle. There's a large number of them. We tended to find that these updates for ECUs updated all of the ECUs or many of the ECUs in the vehicle. We didn't see one where it just updated one or two. It was lots or nothing. It then checked the signature of these hex files. So there was a big manifest file. So noboot.image is transferred. The normal firmware, the CAN gateway firmware, checks that noboot.image is signed. That means that it's a genuine noboot.image from Tesla. It reboots into noboot.image, and because that's signed, we know it's genuine. And finally, that noboot.image checks the ECU firmwares are being signed by Tesla. It's not perfect, but it's pretty secure. Each one of those hex files had a signature. contained within a manifest file that it was validated against. And again, this seemed quite robust. It seemed well engineered. Interestingly, those hex files themselves were not encrypted in any way, shape or form. I converted them into binary, and this is me running an entropy analysis, a randomness analysis across that. Anything between kind of 0.4 and 0.6 is generally code. If it was encrypted or compressed, we'd expect that to be all the way up at the top at 1. Highly random data generally indicates compression or encryption. So they weren't encrypted. Again, I was surprised by this. The next thing it did was perform safety actions. So what it did was it did things like disconnected the battery from the vehicle, made sure it wasn't going to move. Now again, we had access to the log files. That SD card contained verbose logs. So you can hear it's saying open contact to check. Body BMS battery management system contact is open request. It goes through and carries out these safety actions before it does any updates. It then actually carried out the updates. To do that, it had to unlock those ECUs. Now, the way it did that, most of the ECUs in the vehicle appeared to be fairly stock. Probably the exception to that was the body control module, the BCM, which is made by Petron. That seemed to be pretty custom to Tesla, but lots of the other ECUs seemed fairly stock. I'm using standard secure access with UDS. So security access on UDS, UDS is a higher level protocol on CAN, because CAN doesn't do everything you need when you're talking about firmware updates and the like. So security access service ID 27, you need to unlock those ECUs. And how does that work? Well, the CAN gateway says to the ECU, can I have a seed? And the idea there is the ECU generates a random number and sends it back to the CAN gateway. The CAN gateway then needs to take that seed and perform a calculation on it to send the key back. Now that calculation, if it's secret, if we don't know what that calculation is, we can't work out which key corresponds to which seed. The ECU verifies that key. If it's right, it allows access. So it's a really common mechanism with security access. That seed is meant to be random. We've often found it's not. It's either predictable, or if you power cycle the ECU, it will follow a pattern. And the way you calculate that key is meant to be secret. If you let that leak, you can unlock devices. There is a bit of another problem. Once that access is granted, you'll then tend to carry out a firmware update via memory access. The problem is there's no notion of session in UDS, which means that once a device is unlocked on a CAN bus, anything else on that CAN bus can interact with it, and it will think it's just unlocked to everybody at that point. So there's no concept of that session. A rogue ECU or someone connected to that CAN bus can then interact with that ECU themselves once it's unlocked. So that's a powerful tool. We wait for a vehicle or someone to unlock an ECU, and then we've got access to the ECU as if we'd unlocked it. Now we could see that the CAN gateway itself was performing these UDS lock-unlocks without external connectivity. What did that tell us? It told us that the noboot.image contained all of the UDS functionality for all of the different ECUs around the vehicle. So we identified maybe 3 or 4 different UDS algorithms contained within the noboot.image. So again, that leaked information about how to interact with them. So we could see that UDS functionality contained within the noboot.image. So we thought this was quite interesting. The update files are transferred over UDP to that gateway, stored on the SD card. The gateway reboots into the dedicated update mode. Car stops working at that point. You check the firmware signatures on the device in the gateway. Then the gateway unlocks everything with UDS and sends those updates out to the ECUs. There is that chance that you could then inject things onto the ECUs at that point. Some of them did have signature checks themselves, but a lot of them, the firmware was just being sent and accepted. Possibly if there's CRC check. But there was no sign of rollback protection or fail detection here. It seemed that if one ECU didn't take an update, it would just keep on trying again and again. Eventually it would fail, but all of the other ECUs would just stay with their updated version. It wouldn't roll back to the previous one. We're not really sure how the vehicle always ended up in a safe state. It was something we really didn't manage to work out. Finally, there was the bootloader updates. So we looked at the operating system, the application, and the ECUs, but it also had a way of updating the bootloader. Now, Tegra has got something called a BCT, And that's like configuration information. It says how fast does the DDR RAM go? Where do I want to boot from? How do I boot? And things like that. And that's signed using a key that's stored on the Tegra chip. So the idea is it reads the BCT into a little processor called the BPMP, the boot processor. That then copies the NOR flash into SD-RAM after it's configured it, turns on the main microcontroller, the actual Tegra ARM processor, that copies the NAND flash into RAM, and it all runs. But that BCT, that thing that's copied initially, should be signed or encrypted by this key. Yet we found there was a binary on the Tesla that allowed us to update the BCT. So we could take this CID update sample and we could update the BCT. Now, unfortunately, I didn't get time to reverse engineer this fully, but we can infer that that contains that key material to bypass overwriting the BCT. If secure boot had been in place, it would have been possible to be able to bypass it using this. However, secure boot wasn't in place, so that wasn't a problem. So what quirks did we find? Again, back to the bash scripts, we found it was actually possible to update that internal .dat file on the CAN gateway. So you can see here down the bottom, it says autopilot already enabled, autopilot previously disabled. This script was to enable or disable functionality on the vehicle. I don't know if you saw a few years ago, during one of the hurricanes in the US, Tesla upped the range remotely on their vehicles to allow people to evacuate. So Tesla has this ability to update functionality on vehicles. Now, we didn't actually try this. We were too worried about damaging the vehicle or causing it to stop functioning. But other people have changed parameters on their vehicles. It had what we think were how aggressive it would try to carry out firmware updates, starting from negligent and indifferent and yielding, going through to violent kamikaze and suicide bomber. So we think these were kind of like names to say how aggressively it would try to push firmwares through to ECUs. Another interesting thing, the Tesla has driver assist and event data recorder, EDR, and we found that that SD card that's stored on the CAN gateway was actually used as an intermediate staging post. So when driver assist kicked in, it would actually record images. So this is from before we owned the vehicle, someone almost rear-ending another car. I think they braked too suddenly. So we'd recover the images from that. So that's from the EDR. So after all of this, after all the Teslas, you've got to assume that this has got to work. No. This is a friend of mine who, I'd certainly said to him, oh yeah, we've looked at the Model S, like it took loads of firmware updates, we fuzzed the CAN bus and it just kept on working. He bought a Model 3 and it took an OTA firmware update and it bricked it. It completely stopped the car working. They sent a normal tow truck to his house and they tried pulling the car out and they just could not get it to move. You'll notice how small his garage is here. This is kind of like a typical UK garage, not enough room to really even get in and out of the vehicle. So they had to send out this crazy lift that slides underneath, goes under the tyres and tracked and recovers it. So yeah, that pulls out his car. That's what it looks like. The thing was, I think when he spoke to them, they spend quite a lot of their time doing this with Teslas, getting Teslas out of garages that have got stuck. So yeah, it needed to go back to the garage to be fixed. It completely bricked itself, undrivable, which is crazy. So it doesn't always work. So what conclusions can we take from this? Well, the lack of OBD2 pushes owners to directly connect stuff to the CAN bus. I think this is a really bad idea. I think they should have like a diagnostics connector. It's one thing about Tesla owners. How do you know someone owns a Tesla? They'll tell you. People love Teslas when they've got them. And they're enthusiasts. They want to get all this diagnostic information. They used a secure VPN, but then once you were on that VPN, they didn't have a cryptographically strong identity used for all of their APIs, which allowed us to pretend to be other vehicles. They didn't use any TLS for any of those web APIs. Now, it was over a VPN, most of it. But still, it's very strange when you've got a powerful Ubuntu processor that can do all this video processing. Why not just use TLS? They use custom cryptography for the firmware integrity and confidentiality, which is, I think, a poor choice to make. When there's knowing good ways of encrypting and signing firmware and transport encryption. Use them. The CAN gateway does, however, make heavy use of signatures, which meant that we couldn't replace the firmware on it. We couldn't spoof ECU firmware updates easily onto that without access to the CAN buses. But fundamentally, with all of those scripts, some of them that are still used, some of the comments in there, it just feels like it's held together with sticky tape. It's not the same standard of engineering that I've seen on most European and American car manufacturers with ECUs, IVIs, and telematics units made by the mainstream tier ones. So yeah, that's it. I hope you've learned something about the Tesla. I hope you learned something about reverse engineering, some of the techniques we use, and I hope you enjoyed that. And I've spot on finished on 90, which was what I was expecting, so that's good. So if anyone's got any questions, I think Brandon and Sven are going to fire away.
Yeah, at first, so very thanks for this interesting presentation and take us on your journey to show us how you analyze such things in vehicles and which steps you go forward to find the vulnerabilities and the gaps in terms of security. It's really amazing. So let's come to some questions. The first question, did you made also experience with other cars, other vehicles? Do you have some, or can you give us some overview? What are the differences, or what maybe are similar problems in different cars, or something like that?
So I'm not going to mention any manufacturers. Most conventional vehicles still have CAN buses that operate as autonomous systems. So largely the powertrain will be a CAN bus that you will have power modules, battery modules, accelerator, ABS, brakes. Everything will act independently. And if that CAN bus loses communication with the telematics unit or the IVI, it's not too much of a problem. The Tesla's quite different. The CID and the CAN gateway really did act as glue for lots of the other systems around. So we found shell scripts that were doing, there was one shell script that was acting for the automatic rain detection for the wipers. Whereas normally that would be a dedicated ECU connected through to the wiper motors. There would be no need for such a complex system to be involved. We've seen red bend used in other systems. Harman red bend seems quite common in the automotive arena. I think that's really their target market. I think gradually what we're seeing is traditional manufacturers are trying to get to where Tesla are, where you can update all of the ECUs around the vehicle, but they're doing it in a much more conservative manner. And I think they're trying to... Security is only one facet. You've got reliability and you've got safety as well. I feel that maybe Tesla has slightly forgone the reliability aspect of things. Largely that's just a reputational harm. You know, if your cars are unreliable, it's no big thing really, but if your cars are unsafe, that becomes a problem. And I think traditional automotive manufacturers really value safety over pretty much everything else still.
Yep, I can agree. It's also my experience. So coming to one dedicated question, it pops up if you spoke about the JTAG connector. You spoke also that the JTAG connector in the Tesla car was locked.
Yeah.
The question was, from your experience, would it be possible to brute force somehow this JTAG security to find a way to break it?
It very much depends on the chip. So say, for example, we look at a lot of Renesas RH850 chips, you have to send kind of like a fixed ID through to them. I think it's like 92 or 96 bits. It's a funny length, but it's long. It's not brute forceable. However, sometimes what we find is JTAG gets unlocked during the normal operation of the vehicle, and we can sniff those IDs and use them. Generally we're not, if we see something like a password or an ID that we need to send, brute force is going to be out of the question. We try to find gaps in the implementation. So can we just not ask? Can we not send the ID and try reading flash? Automotive, it's really common to find that we can't use generic JTAG adapters. So Renesas, we've got the Mini Cube, the E1, the E2, all of these different JTAG adapters. And what we do is we buy a development board, we look at how their JTAG adapter interacts with the unlocked chip on the development board. We lock the chip, we see how that works, and then we think, well, you know, this JTAG adapter is sending these 8 commands after it's sent the ID. What happens if I just don't send the ID? What happens if I change the order and mess about with things like that? JTAG's just a complicated subject. I wish it was more open, so that we could really understand deeply how those things work, rather than doing black box testing on all of these. So I hope
Thanks.
that
Yep, thanks for these words. So to be honest, there are not so much questions today from the audience. So it could be as simple that you explained everything very well and completely understandable.
Yeah, I'll chime in here a little bit. Andrew, really loved this talk. I think, you know, one thing with reverse engineering, especially in the automotive space, is that there's so much complexity that you need to wade through when you're reverse engineering most automakers' cars. Well, that complexity is there in, I would say, more ways than with a Tesla, because to your earliest point, you know, they have a diagnostic connector. You can plug it into your computer. It's really easy to access. But, you know, as you go through these different layers of reverse engineering and security testing, you're running into things, and you're having to look up data sheets, and, you know, you're having to try and find clever ways to identify JTAG, and, oh, that didn't work, so got to try something new. It's this journey into the unknown of, you know, really being comfortable not knowing things, and then slowly clawing information and assembling that information in a way that ultimately lets you achieve your goals. This is the same thing attackers do. So I loved your presentation. I loved how it carried us all through that journey, all the way to the end, you know, showed us what it looks like to just see bash scripts sitting on a file system, because that is familiar to a lot of people, especially coming from IT security. You wouldn't think that it's just bash scripts that are performing some of these actions, and in most cases in the auto industry, it's not. Tesla, it is. So, you know, given all of that, can you help set the context with the audience here? Tesla put out some really, you know, this is, I think, what, MC1, and then there is an MC2, and then, you know, their M3. The security has been upgraded with each round. From my understanding, this is MC1. Can you just discuss, you know, kind of the differences in the journey Tesla's been on here?
Yeah, so this car was one of the much earlier iterations. I think also the UK tended to somehow be slightly behind the curve in the actual hardware we were getting, but I'm not really sure about that. They've updated their hardware several times, so I believe now they're not actually using ARM processors, and they're not using NVIDIA VCMs. They're using a different module with the same connector. As far as I'm aware, everything has become a lot more designed. I think what you saw there during that talk is almost like agile development. You know, we want a car that we can get onto the market fast, and we can iterate, we can update it quickly. There was that very famous incident. I think it was someone couldn't open their glove box after a crash. He tweeted at Elon Musk, and he pushed a firmware update out in 2 weeks that opens the glove box automatically when you crash, or something like that. You know, they were playing off that, and I think maybe they've changed a lot to realize that, you know, if you update quickly, if you always have these rapid cycles, you're flying close to the sun, essentially, and there will be that downside. I mean, The JD Power in the UK, I don't know if they're global. They do a reliability survey each year, and Tesla was right down at the bottom. But I think they're trying to improve the situation there. The thing was, there weren't really any security vulnerabilities. Or no, there were vulnerabilities. There weren't any exploits. There was nothing serious we could really do without physical access to the vehicle. So although it did feel like it was held together with sticky tape, the end result was a car that you couldn't remotely compromise. Which, you know, that's the scariest thing. You don't want a car you can remotely compromise. That's what you really want to avoid.
Yeah, and so, you know, I think it's this tension of, I mean, Tesla deserves praise and respect for their ability to move quickly, ability
Yeah.
to pull the industry up quickly, ability to, you know, really change the landscape when it comes to EVs and their, you know, appeal at to a mass audience. On the other hand, you know, it's kind of playing with fire. I think the whole auto industry is waiting for this first security incident. And, you know, I think many automakers are much more hesitant and skeptical, slow moving for that reason. You know, they're trying to avoid that first incident from ever happening. Whereas Tesla has the move fast and break things, and, you know, we'll deal with that when we get there kind of attitude. And
Yeah.
you know, it's tough. It's tough to understand what's right and wrong. But
It's very much a balance, because I mean, if we look to some of the work that's been carried out even against BMWs, there's people after a lot, 16 people working for 10 months have found really, really impressive vulnerabilities in cars. But at some point, there's going to be a vulnerability that is easy to discover and easy to exploit. And Tesla's got the massive upside there that they can fix that vulnerability in days. Whereas you look to other auto manufacturers, and we're still talking, returning the car to the garage to get the update. It's definitely a balance. It's got two sides. I'm not sure which one's the right one.
yeah, and that's for us to comment on, but not to decide in any way. So we'll see. We'll see how it kind of plays out here. But a question from kind of the audience here, and really relevant to the ASRG, because the ASRG, it's a big community. We're trying to get more people involved in this, lower the barrier of entries to car hacking, make resources available so that maybe you don't need all the tools in the world or whatever. What is the time investment here? What is the time and money investment to perform this research? How long did it take you, and how much did it cost you and your company, if you can share?
So that was 10 days of work, including ripping the car apart several times. The tools that we use, oddly with the Tesla, a lot of what we were using there was very conventional information security tools. One of the challenges we get is when you start hitting the CAN bus. There are low-cost open source tools, but they don't do high-speed CAN buses. They don't do CAN FD. They struggle a bit. We personally use the Cavesa equipment. There's Peak, there's Vector, there's lots of others. But that's one of the things that we've really struggled with is getting tools to work with CAN that are usable and low cost enough. I think one of the interesting moves we've seen is, my first dedicated automotive test was 2016, and that was done completely black box. So we were working on behalf of the manufacturer, and they gave us nothing. They didn't give us it. They gave us a technician who was very good at taking the car apart and getting us access to ECUs, but we had no firmware. We didn't have documentation of the CAN messages. Everything had to be reverse engineered. Whereas I looked at a scoping call I had last week, and we got a PowerPoint from the tier one saying we'll tell you the CAN messages, we'll give you the schematics, we'll give you 4 devices, 2 of which will be unlocked. We'll send you a JTAG adapter, you'll get test harnesses. Like, that opening up of devices is making things much more, it's getting rid of that obscurity that stops us finding those deeply hidden vulnerabilities, the really high impact things. And I hope it continues to move like that. We've certainly seen that IoT and phones and stuff.
Yeah, certainly that's true for service providers like pen test partners. You know, we see the same thing. We're getting just much better testing setups, much more information that enables us to do more advanced research. Now, there's a second bridge there that still has yet to be crossed in any meaningful way, which is how are you now extending these tools and ease of usability and, you know, less security through obscurity or security relying on obscurity, so that you're enabling researchers. Sure, you're enabling attackers, but you're enabling researchers, the open source community, you know, the hacker community, to really be doing a lot of this work. Because if automakers are just paying service providers like you and I to do this work, no way you're ever going to find every hole. No way you're ever going to get it up to a security posture that it needs to be. There's just not enough hands working on it. So I'm a big advocate of, hey, we got to work towards a tool environment that works for the community.
It's an interesting one, because you've always got that barrier of having to buy a vehicle at the moment. You know, it's quite rare, especially nowadays. You can't just buy an IVI on eBay and connect 12 volts in ignition and expect it to do anything meaningful. It might power up, but it's probably going to be expecting the BCM, the TCU to all be present with a wiring loom for a vehicle bought on eBay, if you can get them, they cost a fortune. I mean, I think someone said they're like 8% of the cost of a new vehicle or something anyway. You know, it's having that access to start with is really complex. Now, I can't speak to all auto manufacturers, but one thing that we've seen is that they produce a car in a box, and it's not everything. You know, it's not every ECU, but it will be the telematics unit, it will be the IVI, it will be a board to simulate inputs from the wheels, and, you know, just to give you that experience where you can actually start testing stuff. And if the manufacturers could hire or loan them to researchers, I think that would be massively powerful. You know, being able to
the pasta box.
Not specifically that. It's a similar idea, but auto manufacturers have made the same themselves. We've got one in our lab, and it's been absolutely invaluable, because it's big. It's still, you know, the size of a huge suitcase, but to demonstrate, to teach, to find vulnerabilities, it's very useful.
Sure. And to inject my kind of take on that is, you know, a different alternative would be making these kind of things remotely accessible. And of course that comes with challenges, but then that way, again, you're giving access to, you know, that great researcher that is somewhere in the world that maybe doesn't have the resources to do it, but certainly has the skills.
Yeah, I think that could work, certainly.
So yeah,
I mean,
let's see. One more question from the audience that's just popping up here. So did you guys, you know, I know a lot of people in the Tesla hacking community, and it just kind of chuckle about being able to enable features and stuff. And you talked about that a little bit. Were you able to do that? You know, get the sport mode or the quicker acceleration or full self-driving or autopilot where you didn't pay for it?
To be honest, we didn't try. We saw that script, and so a kind individual from one of the Tesla communities gave us his firmware dump as well, which was really valuable because he'd stopped firmware updates on his. So he had like a legacy image that was a long way behind ours. Again, it had little clues in it. You know, there's things that complete the puzzle. But at that time, people were certainly enabling things that, you know, they hadn't necessarily paid for. I mean, I think that's fascinating that we're absolutely accepting of buying software and paying more for the same software that does more. So, you know, you can buy Windows Starter Edition, you can buy Windows Full Edition, Windows Enterprise. You know, we expect with software, we pay more, we get more, and it can be kind of the same fundamental product. But with cars, we're still in this mindset that I've got the physical car. If it can do 190 miles an hour instead of 170, I want that for free. And I sympathise with that, but at the same time, like, I can see why car manufacturers want to go down this software limited path. I mean, I think the risk is with EVs is the batteries can get, you know, they can suffer long-term damage or instantaneous damage when you push them too hard. Whereas like the car tuning community with internal combustion has always been able to kind of remove all of those electronic controls if they want. Maybe not remove all of them, you know, but it's I don't know. I wonder where tuning of electronic cars is going to go. The motor's fixed. You can't really do much with the motor. What can you do with the electronics? You can't chip a Tesla. You can give it more that they already intended to give it, but yeah, it's the psychology of it.
You see people doing all sorts of crazy things, like installing different batteries and larger batteries, and you know, upgrading motors and stuff. So I think it does kind of have that aspect of tuning and building and having to reconfigure the software to, you know, fit. You bought a P80 and now it, you know, you essentially turned it into a P100D. And so
Yeah.
getting the software to play nice with that is another reason to do it. So one final question and then we'll close out. So Peter's asking about this race between, you know, features coming out and, you know, highly connected vehicles and attackers. You know, the reality is that there aren't, the concern is nation state hackers, and there is nation state activity in terms of looking at how to use the attacks against vehicles as a form of warfare, cyber warfare.
Yeah.
What do you see that race as? I mean, is it that the manufacturers are going to release features and secure them adequately, and maybe we'll never see this kind of attack? Or do you think the well-funded researchers will start to see these attacks come up no matter what? I mean, I guess what's your take on that?
So my feel there is that if we look back 10 years ago to normal information security, the concept of ransomwaring a hospital, just, it wasn't even really in our minds. I don't think we're very good at predicting the future. The thing is that as a nation state, if I could disable every single Ford Transit van in the UK, that is going to have serious impacts to the UK. You know, 30% of workmen and deliveries aren't going to get to where they need to go. So as cars become more connected, you have this massive risk, denial of service to thousands of vehicles. The thing is it was said with nuclear safety back in the 70s. We've got two modes: complacency and panic. So we become complacent. You know, we make these updatable cars, and like, no, the Miller Valasek Jeep hack, epic, amazing work, but it was like a perfect storm, and we haven't seen anything like it since. So that idea of remote control of a vehicle, I don't think it's going to come along particularly often. But the problem is, what happens if it does? What happens if someone does gain access to every vehicle of a particular brand and bricks all of them? I've got no way of predicting it, to be honest. It scares me.
I think I fall victim to the same thing. You know, this attitude that the attacks are gonna look like, oh, someone's going to steer you off a cliff. No, in reality, it'll probably be more monetarily motivated. Like, hey, we'll unlock all, your example, Ford Transit for if you just send, 100 million in Bitcoin to this wallet.
Yeah.
And that certainly if there's money to be made, the attacks will come. And I think the auto industry is doing well recognizing that they're not going to stop everything, and you got to be prepared and have mechanisms in place to respond to incidents. Otherwise,
Yeah.
this VSOC, Vehicle Security Operations Center, has taken quite a bit of that concept has gotten traction. So that's good. That's really good. At least we're not waiting to say, oh, well, we should have been able to respond to this, and then
Yeah.
started the journey.
I mean, I think what you said there is absolutely key. So that we've got a framework in the UK, and there's one with NIST: predict, prevent, detect, respond. And I think the automotive industry in the past has just been preventing. They haven't really been doing the predicting very well. So they've not really been judging who the threat is, what the threat is, and the detection and response aspect of it has been almost absent. And, they, like you say, having a VSOC to be able to actually detect and react to events is probably going to be vital. I mean, I can't think of. You think of the largest IT networks in the world, and they're probably smaller than the number of. If you look at the top 10 car manufacturers, Ford, Chrysler, they've probably got more cars out there than these IT networks have got computers. They're huge.
Yeah.
Okay, I would also raise one final question from my side. It's more related to your experience and your professional work. So if you look on the products that we use in the automotive industry, I think from my opinion is that logging the debug ports is one really important measure that we should bring in place in the products. But do you have some recommendation with your experience? What would be also such a powerful measure? What we should take care if we develop such products or bring the products in the market?
So I think that the automotive arena needs to look to those low-cost fundamentals, like locking the JTAG port. It's easy to do, and it is an obscurity step. It might not be the best thing in the world always. If I'd rather you lock JTAG, but also put your firmware out there for researchers to look at. But at the same time, things like making sure that when you build your binaries, that they don't have debug symbols in them. Make sure you use things like ASLR, address space layout randomization, so that if you do have buffer overflows in your devices, they become harder to exploit. Minimizing the attack surface. I mean, it's really common for us to find that IVIs are just running unnecessary services that they're never going to be used day to day. I mean, the really common one a few years ago is you could plug USB Ethernet dongles into IVIs and you'd get an unfirewalled connection into the IVI. There's all these, it's these basics I think people need to really focus on to start with before they start thinking about the more complex things. But second to that, we call it pushing left, secure by design, this kind of concept that right from the outset you try to build your devices securely. But the problem is when you're looking at a car, you might have 10 different tier ones making different ECUs. It can become very difficult making sure that everybody's speaking the same language. Those specifications you give to them are define security well enough that they can implement it. It's a challenging one. I'm not sure if there's any silver bullets.
Yep, but thanks for your opinion. I agree totally. And yeah, let's do our best to protect our products on the one side and make your work then afterwards more interesting, more challenging.
Yeah, I'm always up for an interesting job.
Well, guys, with that said, we better close out here. I think we're a few minutes past. YouTube and Google may kick us off. Andrew, I really appreciate you giving this talk. I thought it was really great. Would love to have you back or anyone from your team. So, just reach out to us anytime. And yeah, with that said, everyone, thank you for joining. Thank you for listening in on these and making these a possibility. If you don't keep viewing them, we wouldn't keep making them. So really, keep checking out the webinars we have upcoming. They're really exciting. And with that said, we'll close out. Thanks, everyone.
Thanks very much.
Okay, and we're offline.